Okay, so imagine you're a staff engineer at a major tech company. You've just been handed an absolutely massive project. Download the internet, or, a huge chunk of it anyway, to train the next generation of AI. So where do you even begin?
First, let's wrap our heads around the scale here. We're not talking about a few thousand websites. We're talking about 10 billion individual web pages. To put that into perspective, if you visited one new page every single second, it would take you over 300 years to see them all.
And to make it a real nail-biter of an engineering challenge, you've got a deadline. All this data needs to be collected and ready to go. And here's the kicker. You've got to do it all in just 5 days. The clock is officially ticking.
Now, this isn't just some fun thought experiment. This is a real-world system design problem that search engines and AI companies grapple with every single day. So, if this landed on your desk, how would you tackle it?
So, over the next few minutes, we're going to architect this system from the ground up. We'll start with a really simple first draft, watch it break, and then piece by piece add the fault tolerance, the speed, and the intelligence it needs to actually work at this insane scale.
All right, let's get our hands dirty. Every complex system starts with a simple idea. So let's sketch out the most basic blueprint for a web crawler that could, in theory, get the job done.
The logic seems almost deceptively simple, right? You start with a list of URLs, what we call a frontier. You grab one, you fetch the page, save the text, and then you find all the new links on that page and add them right back to the list. It's just a simple, elegant loop. But this beautiful, simple design has a fatal flaw when it meets the real world.
See, the internet is like this vast, untamed wilderness. It's messy, it's unpredictable, and sometimes it's just plain uncooperative. Our simple little crawler is like a hiker setting off with no map and no compass. It's absolutely going to get lost or fall into a ditch. We have to build something that can actually survive out there. Seriously, think about it. Imagine you're halfway through crawling some huge website, and your single crawler program just crashes. Maybe a network hiccup, maybe a bug in the code. What happens to the URL it was working on? It's just gone. All that potential work is lost. And at this scale, starting over is not an option. Now, a naive approach might be to just, have a timer in our code that retries. But what if the whole machine crashes? That timer's gone. A much more robust solution is using a managed message queue, like Amazon's SQS. Think of it as a smart, shared to-do list for all of our crawlers. The key difference here is that the queue manages the state, not our fragile little application.
And what's really cool about this is how it creates a self-healing system. Here's how it works. A crawler grabs a URL from the queue. The second it does, SQS makes that message invisible to everyone else for a set visibility timeout. This is genius, right? It prevents two crawlers from doing the same work. If the crawler succeeds, it tells SQS, hey, I'm done, delete the message. But if it crashes, the timeout just expires, the message magically reappears in the queue, and another healthy crawler can pick it up. And if a URL fails way too many times, it gets shunted over to a dead letter queue, so an engineer can check it out later, all without stopping the entire system.
Okay, so beyond just surviving failures, our crawler needs to be a good citizen of the internet. Think of it like being a guest in someone's house. You wouldn't just barge in and start making a mess, right? You'd be polite. We can't just hammer a single website with thousands of requests a second. That's basically a denial of service attack, not web crawling. And this whole concept is known as politeness.
Luckily, most websites give us a little rule book in a file called robots.txt. It tells crawlers which parts of the site they can visit and how often. So here, user agent asterisk just means these rules apply to everybody. Disallow tells us which directories to stay away from, and crawl delay is a direct request. Please wait 10 seconds between each page fetch. Respecting this isn't just nice, it's non-negotiable for any legit, large-scale crawler.
Okay, now let's talk about speed. We've made our system robust and polite, but all that politeness, it costs us time. We are simply not moving fast enough to hit that 5-day deadline. We need to go from a crawl to an all-out sprint. Let's do some quick back-of-the-envelope math. If we're optimistic and say it takes about 2.5 seconds to process a single page, including those politeness delays, it would take one machine nearly 31 days to crawl 10 billion pages. Way too slow. To get under our 5-day target, we have to parallelize. As you can see, with 8 machines working together, we can get that time down to just under 4 days. The answer is obvious. We need a whole fleet of crawlers. But if we just throw a bunch of machines at the problem, we're going to hit a really surprising bottleneck:
Early research into web crawlers found something shocking. Up to 70% of a crawler's time was spent not downloading pages but on DNS lookups. DNS, the domain name system, is basically the internet's phone book. It translates a nice name like example.com into a machine-readable IP address. Every single request to a new domain requires this lookup, and it's this hidden tax on our time that adds up incredibly fast.
So how do we solve this? Well, first, aggressive caching. Once our crawler looks up an IP address, it needs to remember it, store it in a local cache. That way we don't have to keep asking the phone book for the same number over and over again. And second, we shouldn't rely on just one DNS provider. It's like having multiple phone books. If one is busy, or maybe it's rate limiting us, we just use another one. By spreading our requests out, we distribute the load and avoid any single point of failure.
Okay, so we're fast, we're resilient, but we're still wasting a ton of time and resources. A huge amount of the web is just redundant, and we need to make sure our expensive crawling effort isn't spent processing the same content over and over.
See, just tracking which URLs we visited isn't enough. For instance, you could have two totally different URLs, one with www and one without, that both point to the exact same homepage. If we're not careful, our fleet of crawlers could fetch and process the same page twice. We need a way to detect this duplication at the content level.
So the crucial point here is picking the right tool for the job. A classic computer science answer is something called a Bloom filter, which is a super fast way to check if you've probably seen something before. The catch is that probably, it's not 100% accurate, it can give you false positives. Honestly, a much more practical solution these days is to just hash the page content and store that hash in a database with an index. It's 100% accurate, it's way simpler to implement, and modern databases are ridiculously fast at this kind of thing. And finally, we have to protect ourselves from what are called crawler traps. These things are like quicksand for our crawlers. Once they fall in, they can never get out. Just think of a website with a calendar that lets you click next month, literally forever. A naive crawler would follow those links into infinity, wasting all of its time. The simple fix? Set a maximum crawl depth. We just keep track of how many clicks away from an original starting URL we are, and if we go too deep, say 20 links, we just stop following that path.
We've gone from a simple little loop to a pretty sophisticated distributed system. It's been quite a journey. So let's step back for a second and boil this whole design down into a few core principles that apply to almost any large-scale system.
And here's what it all really boils down to. Building at this scale is less about one brilliant algorithm and more about a whole philosophy. It's about isolating failures so one bad part can't take down the whole show. It's about being polite, finding the real performance bottlenecks, not just the ones you expect. It's about eliminating all that wasted work and, probably most importantly, designing a system that can recover from errors automatically without a human having to wake up at 3 a.m. to fix it.
So we've designed a pretty powerful crawler for the web as it exists right now. But the internet is always changing. So I'll leave you with this question. What do you think the future of the web is going to look like? What new challenges will it create for crawlers? Is it going to be more complex JavaScript apps, decentralized content on new protocols, or something we haven't even thought of yet? The core principles we talked about will probably stick around, but the problems themselves, they're always going to evolve.